Hello and welcome to Chemistry for the Interdisciplinary Sciences. My name is Dr. Felix Janeway. I'm going to be doing the video components of the first semester of this lecture series, and there'll be another member of staff who will be doing the live components of the lecture series. Today we're starting on chemistry right from the top, and so this is lecture 0. Hopefully you'll be seeing this in induction week, but I'm not entirely sure. During this course, I've provided tutor notes. What I'd like you to do is try lots of different ways of taking your notes while you're listening to these videos. Make sure you're really active. It's very easy to just watch it and then go, yeah, I understand that. It's much, much better for your learning if you take notes as you go along. So please do. So what is chemistry? Probably you're used to it looking a bit like this, right? Some explosions or looking at a flask keenly. You can see that I've got two different people looking very carefully at flasks, which, to be honest, we don't often do as chemists, unless we're looking at crystals. But chemistry is way more applied. You'll have come across it a lot more in your real life with its actual applications. So here we've got things like medicines. If you think about aspirin for a second, that's a molecule that you take that gets rid of your headache. What an incredibly specific thing for a molecule to do. There are other molecules that do other things, of course, lots and lots of other drugs, and then things like alcohol and so on. A very specific shape there of a molecule seems to have a specific effect on the body. Chemists also make materials, so we got things like the nylon that's in this slide here, but loads of other materials. Glass that absorbs lights, glass that shatters into a million tiny pieces, Kevlar, all sorts of different materials, even conductive plastics nowadays, all designed by chemists and material scientists, really. The atmosphere, we know that climate change is a great big topic at the moment. Taking measurements of the atmosphere is very difficult, especially if you want to see the whole atmosphere. You need to take the measurement from the outside or else bounce a light from inside to outside and back again. So taking those measurements is in itself a chemical principle. Designing the equipment that can take those measurements, interpreting what exactly is there based on the measurements that you take, even to the point of like flying through a cloud or flying through the atmosphere to figure out what's happening in it. We know that the food is a big issue now for the globe, and so chemists can be involved in things like offering substances to change the soil and the fertility of the soil, the fertilizers in there. And again, we know that there are issues with fertilizer use, so again, balancing those needs and those impacts on the environment really important. But then also things like pesticides, making sure that a larger fraction of the crop that is grown is actually useful for food, is an imperative for most people, not only for the business of actually making food and selling it, but also for the ethics of creating as much food as possible. There are other uses, more frivolous things you probably hadn't even thought about really, things like surfactants, soaps. All of the cosmetics industry is humongous at the moment. Yes, it might seem frivolous, but it isn't. It's actually a very complex and difficult system in there. We got formulation chemists, people who are trying to make substances that are the right texture or composition, thickness, drying at the right speed, things like gel nail varnishes, for instance, all sorts of different and really interesting chemistry going on there. So chemistry is all about basically finding an application and finding a substance that will do that application, if you want. So today we have a few learning outcomes. All I want you to be able to do at the end of this lecture, and generally in a lecture series I'll give you these learning outcomes here. I want you to explain the term periodicity. I want you to know where the groups and periods are on a periodic table and describe how those elements are grouped by properties. And then I also want to identify 3 different blocks of the periodic table, though there are 4. I'm going to show you the 4th as well. 3 different blocks in the periodic table. And for now, you don't have to understand why they're called that or anything. That's going to be in future lectures. So let's just start by looking at the atom. Now, this cartoon is completely inaccurate for reasons I'm going to show you in the next few lectures. But for now, we can have a look at this atom and say, okay, it's got some solid in the middle, and it's got something whizzing around the outside. And that's essentially correct. And so that's how I want you to think about an atom in your head. It's got this central bit, which we call the nucleus there, and these electrons going around the outside. If I go back to my original background picture, you can see a slight issue here, look at this. What is this whizzing about? It seems to be the same size as these. In my cartoon, it's just as bad, essentially. These electrons here should not be the same size. So let's have a look at actually what these particles are and what properties they have and how that affects the chemistry of these atoms. So the first thing is that most chemistry that we're going to study, we're going to look at a little tiny bit of radiochemistry, but most of the chemistry that we're going to study this semester is to do with where are the electrons? Are they going away? Are they coming on? What's happening? Where are the electrons moving to? Are they being shared? What's happening? And so the thing that we mostly are going to be looking at is electrons. Where are they in the atom and so on? The electron has a negative charge. And for now, if you don't mind just accepting the idea of charge as a principle, and two things that have the same charge will repel each other, two things that have opposite charges will attract. If for now you're happy to accept that, that would be very helpful. So an electron has a negative charge, and it has a negligible mass. It's actually 1/2000th of the mass of a proton or a neutron in there. So it's a very, very small thing. It should be way smaller on my diagram than it is, but never mind. Still seeing the principle there that the electron is smaller. Inside the nucleus, we have the oppositely charged particle. We have a proton. Protons have positive charges and they attract electrons. In a normal element, the number of protons and electrons will be equal because you want the charge to overall be zero on that atom. So the number of protons in a nucleus is going to define how many electrons you get around that atom itself. Finally, we have, I should say the mass of a proton is basically 1. We're going to say these masses relativistically. So what I mean by that is that the mass of a proton is 1. It's the same as the mass of a neutron. Of course, that's not 1 gram. That's just 1 unit, if you want. So the proton has a positive charge. It attracts electrons that have a negative charge. And then we've got this last thing here, the neutron. Now, the neutron's job is basically to stop all the protons from flying away from each other. Because they're all positively charged, they don't want to be in a nucleus together at all. And so they need a sort of glue to hold themselves together. And those are neutrons. So neutrons and protons are attracted through a different force, not electrostatic charge, which is positives and negatives, but strong nuclear charge itself. What that means is that the neutrons are kind of the glue that hold together those protons. So let's just go through all that again. The number of protons changes the number of electrons that are going to be around an atom, and therefore its chemistry. The number of neutrons doesn't really matter. We just need enough glue to hold those protons together. And so an atom of any element can have a variable number of neutrons. We're going to have a look at where exactly those boundaries are later on. But the number of neutrons doesn't particularly matter to the chemistry of the atom itself. So here's a starter question for you. I want you to just have a quick think. This is the periodic table here. Why is it called the periodic table? In what way is it periodic? What does that mean? So I'd like you to just pause the video now, have a think about it, and write down a few ideas. Really important you write down the ideas, not because you're going to send them in or anything, just so that you have actively had a go at the question. So pause now. Okay, I'm going to assume you've paused. So why is it called periodic? Well, a period is an amount of time, isn't it? We say, the Elizabethan period or whatever. But a period has an even more specific meaning, and I should have prepared a pendulum, but never mind, I'm in my bedroom. I have a spoon, obviously. Imagine we have a pendulum here that is swinging, and imagine that I'm not powering it with my hand. The period is the amount of time it takes to get from one end to the other and back again. And so what we might say is that period is the amount of time it takes for it to sort of complete a loop, if you want. A loop being going to the end, coming back, and then starting all over again, going forwards and backwards. The periodic table is very similar. It has looping patterns that happen over and over again. So we could have the periodic table looking like this. And here on the periodic table, the small numbers under each element is the number of protons in the atom. So what you'll notice is on the periodic table, there's one of all of them. If you have a nucleus that has 1 proton, well, that's a hydrogen. If it has 2 protons, that's a helium, and so on. So notice that the periodic table is ordered basically by the number of protons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. After 10, it goes to 11. So the end of the periodic table here, it should be hooked up to this side, and so we might represent the periodic table like a spiral, like this. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and so on, going around and around in this sort of spiral system. The only real benefit to that is to show you that helium and lithium are very similar to each other in terms of it being next to each other in the proton number. However, the periodic table is drawn like this because it shows there's a way more easy to see set of elements that are ordered together. So the arrangement of a periodic table is basically, all these elements are the same, have the same character, they do the same thing, and all of these elements do the same thing, and all of these, and so on. So all of these different elements do the same thing, and that's why it's got this funny shape. Notice the periodic table has like a pair of horns at the top, and then it's got this sort of row that's quite short, and then another short row, and then a long row, and a long row, and so on. At this point down here, where it's lanthanum, that's where we should insert all of these. There should be a little gap in between that periodic table, and it'd carry on like that. So the periodic table has a really specific shape, but why? That's what we're going to answer in the next few lectures. Why is it that it has this shape? It's all to do with the chemistry of these molecules. Of these elements, these atoms themselves. I'm going to define that term molecule later on. So what do I mean? What I'm suggesting is that elements in a row have very similar properties. So let's look at one that we're probably used to. You've probably all bought a party balloon or something like that. That's helium. So when you have helium, you can breathe it in. You've probably done that experiment. You breathe it in and your voice goes all squeaky. That suggests that helium is safe to do that with, doesn't it? If you were to breathe in chlorine, for instance, you'd be in a coughing fit immediately. It would kill you if you breathed in a balloon of chlorine. But breathing in a balloon of helium is absolutely fine. And they're not very far away from each other on the periodic table. Now, because these elements are arranged in rows, what that suggests is that each of these elements must have the similar properties. Neon must be similar to helium, and argon must be similar to helium. And so what you would expect, let's say, for instance, if I got xenon. If I got some xenon, it should be safe enough for me to breathe in, because it is in the same period as helium and neon and argon and so on. They should have the same properties. So let's have a look. I have a video of me doing this last year, so let's check it out.
Hopefully most of us have seen the experiment where someone breathes in helium. What happens? It goes all squeaky and high. And the reason for that is that the helium gas is much less dense than the air that you're used to talking through, if that makes sense. So the helium gas allows sounds to pass through it much quicker than normal, because it's so light, it just passes on that message. And so all the waves get squashed together and it sounds much lighter, or much higher, sorry. In this case, xenon is way, way far down. I didn't throw this balloon around because at the moment xenon is very expensive, but you can feel the gas in here. It feels very odd. And so I'm going to breathe it in and we'll see what happens.
So now that I've breathed in the xenon, you can hear that there's a significant difference in pitch.
Everyone with me? There's a... So the other thing about xenon is it hangs out in your lungs. It's so heavy that me just going does nothing. I've got to bend right over and get it out. Okay, we're good.
So the xenon there had the same property as helium, didn't it? It was breathable. It also changed the pitch of my voice. Helium went up, xenon went down. The reason for that is that the density of the air is somewhere in the middle, similar-ish to argon and neon. Helium is lighter than air. Xenon is heavier than air. So in fact, if you have a balloon of xenon and drop it, it just goes straight to the floor and it sort of goes poof like that. It's very odd. So in the periodic table then, what we're sort of seeing is that these elements do have very similar properties to each other. And their properties are changing going down the column there. But they're the same. They have been organised to be the same. And that's what the periodic table does, really. It puts together elements that are the same, and then the shape actually tells us something about the structure of the electron paths, if you want, that go around it. And again, we're going to talk about those later. But let's just go straight to, then, one of our learning outcomes. What we have is groups of the periodic table. So elements are arranged together in groups, and those groups go up and down in the periodic table. And again, this is to do with the electronic configuration of those elements in there. So our groups are going down. All the elements in the same row will have similar properties to each other. And if we have a little look and see if we can see any that make sense, look at this: copper, silver, gold. Silver and gold, very inert metals. Copper's a pretty inert metal. It's not completely inert, but quite inert. So again, we're seeing those similar properties. Let's have a look at another set of properties. We've got lithium, sodium, potassium, rubidium, and so on. Let's have a look at how these elements work in a short video.
Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
So we saw quite a reactive set of elements there. These ones are not inert, unlike neon, 10 protons, sodium, 11 protons, all of a sudden really reactive. Not a gas anymore, a metal for some reason. Again, we're going to define that going on. And a metal that's very different to others. If I just got this steel can and popped it into some water, it wouldn't react anywhere like that. So all of these elements are reacting in some way. Similarly, they all react with water in a similar way. But you'll notice as we went down the periodic table, we started to see them get more and more reactive. They were more and more ready to do that reaction. So that suggests that whatever's happening with these elements in the first row here, they must be doing something very similar, but it must get easier and easier for that electronic transition to happen as we go down the period. As we go down the group here. So those are groups going up and down there. Whoops, in the periodic table. Those are our groups. There we go, groups. Now the periods are going across, you won't be surprised to hear. So that is, how many elements does it take until you get that property back? So if you think about this, if we're saying hydrogen is similar to lithium, and then it takes one element to go from hydrogen to lithium, then there are 8 in between lithium and sodium, and then there are another 8 between sodium and potassium. These are the periods then. The rows of the periodic table are our periods. How many elements does it take to get back to that property that we've seen before? And it doesn't have to be the first one. We could think about it being like a noble gas, like group 0 or 18. And in fact, we haven't talked about that, so let's just quickly pop back to that. Groups, how do you name them? On this periodic table, they're 1, 2, 3, 4, 5, 6, 7, and 0. You can say 8 if you want, that's absolutely fine. 8 or 0 are both okay. Now you might be thinking, well, what about these ones in the middle? Well, the answer is that actually these are 3, 4, 5, 6, and so on. And this one is 13, 14, 15, 16, and 17. You're just going to have to get used to the fact that in chemistry, there are usually quite a few different naming systems. I would like us, in this course, just to use this naming system, because we're not going to be thinking too much about these elements other than their basic electronic configurations. They get a bit complex anyway. So those are our groups going down, and those are our periods going across. Now the periodic table has that weird shape, but we can lump it into basically 4 different little rectangles. There are actually some elements missing over here, but because they're so radioactive, chemists aren't bothered about them. If I can't make a molecule, I don't care. So we have this block over here on the left. That is the S block. You don't have to know why it's called that. Just for a second now, if you don't mind accepting, that is the S block. And we'll find S block elements in there. In the middle here, we got the D block, the transition metals. Then over here, we got the P block. Now, again, you don't need to understand why they're called that yet. I am going to explain that in the next few lectures. But for now, these are the S block elements. These are the D block elements. These are the P block elements. And at the bottom here, we've got the F block elements. We're not really going to deal with them very much. We might see a couple of nuclear reactions with them, but you don't need to know that those are the F block elements. I'm just showing you so that you've got the complete picture. Now we can go a little bit further. We can sort of look for some more patterns, and we can get even more precise about this. We can start talking about the names of the groups. So we have group 1 and group 2, the alkali metals and the alkali earth metals. Again, we'll talk about why they might be called that. We got our noble gases. Those are our gases that don't react. They're called noble because they're like fluty and just don't want to talk. No electrons for me, thank you, is what's going on over there. And we've got halogens there in group 7. So you can imagine this gets more and more complex as you start breaking the periodic table down. For now, I just want you to concentrate on S, P, and D blocks. So that takes us to the end of the lecture. What I'd like you to do is, without looking at your notes, have a quick go at this set of 5 problems. So don't look at your notes, just from memory what's going on. So if you'd like to pause now and give that a go. Oh, and I'll get out of your way. That seems like a good idea. Pew. Lovely. So I'm going to assume that you've paused now, and I'm going to move to the next slide, which is looking at your notes. So please, can you have a quick look at your notes, see what you've written down, and see if you can answer these questions again. So I'm going to pause that for you now. Okay. If you haven't had time, please do pause and have another little think. The idea at this point is to have a look at what were the quality of your notes. So how did you write notes? What information did you get out of them? So this first question, if the mass of a proton is 1, the mass of an electron is. Now notice on the slides, I didn't say what it was. I just wrote negligible. So if you were looking at your slides, you still wouldn't have had an answer. But I did actually say out loud that the mass of an electron is 1/2000th of the mass of a proton. And so that means the correct answer here was E. Now, of course, I don't expect you to remember that number. This is all about whether or not you took good notes. So if you took a note that said 1/2000th, and then you converted that over to a decimal there, then brilliant, that's great. You've got all the information out of the lecture, even the things that were said but not written down. Fantastic. You might have said A because you remembered the number 2000, but you weren't quite sure what that is. Great. If you remember that number, that's fantastic. Again, you want to have this written down so that, in a couple of days, you do still remember that. The central block of the periodic table is, well, it's this one that's shaded in here. That is the D block. So D is the correct answer there. So you might have been able to do that without your notes if you just remembered it's S, P, and D. S, D, P, if you want. S, P, D, whichever way around you want to think about it. In there. The periodic table is arranged in order of. A couple of correct answers here, I would say. The number of protons is specifically how the periodic table is designed. So D is the correct answer. But, to be fair, the number of protons dictates how many electrons there are in an atom. So I'd also accept A is arguably correct, though, again, this is an elemental form of the atom. And you might also have said E collected by properties. That is the case, but it's the shape of the periodic table has been dictated by the properties. The order has been dictated by the proton number. So technically, I would say that D is the correct answer there. Looking at the same group as we go down the periodic table, atoms get more reactive. Well, that was certainly true in that video. So that might be true. But what we didn't see is that in group 0, helium, argon, neon, and so on, we didn't see xenon being more reactive than helium there. So that suggests to us that it's not always true that they get more reactive. Have more mass. Yeah, they certainly do have more mass because they have more protons. So if there are more protons, they must have more mass. The nuclei themselves must be heavier. Of course, this is assuming that they have the correct number of neutrons. It is possible for an element with a relatively small number of protons to have quite a large number of neutrons. That is possible. So it's not always going to be the case that they have more mass. Are more expensive? We didn't even talk about that. Generally, that probably is true, but that is just because if they get more reactive, they get harder to extract and so on. They do tend to be rarer, but it's not true that that matters really, are more expensive. Get larger in volume. Yeah, that's certainly true. As you go down the period, they do get larger in volume, but I don't know how you would know that yet. And so again, D is a correct answer, and you might already know that from some previous study that you've had of chemistry, but don't worry if you don't know it now. I didn't talk about it. E are more unstable. That, again, seems to be similar to get more reactive, but they are actually very slightly different terms. So I would argue that B is correct and D is correct. So either of those is fine. Again, this isn't about how many you got correct. This is about how did your notes help you to get these correct. So I do want you to have a very quick think about, did my notes actually help me do that at the end of here? Again, these are not the sort of questions I'm going to be asking you too much. They're just sort of recall questions from the lecture. But I do want you to think about your notes and how they helped you out. And maybe try something different in the next lecture. So that takes me to the end of our lecture. Best of luck, and I'll see you very, very shortly for lecture 1.